recording. Okay, so well, so today it's our great pleasure to have Pavel Kovtun give the colloquium, and so Pavel is a professor at the University of Victoria, and he's very kindly woken up at 5:30 in the morning to talk to us. And so Pavel did his PhD at the University of Washington, and he did a postdoc at the Kavli Institute of Theoretical Physics at Santa Barbara. And he's well known for being the K in the KSS conjecture. So that's a Kovtun Son Starinets conjecture, which is basically places a lower bound on how viscous a fluid can be. And this has created a lot of activity surrounding this work. And today he's going to tell us about pushing the limits of hydrodynamics. Oh, and I forgot to say, so first of all, in terms of questions, please, if you have questions, you can just ask directly. And also, Pavel asked to please, whoever can, to please keep your cameras open so he can see us.
Thank you. Thank you, Daniel, for the introduction, and thank you to everyone in the physics department for inviting me to speak. I have visited the Technion a few times, and I have enjoyed my stay tremendously. And it's good to visit even virtually. So, as you can see, the title is Pushing the Limits of Hydrodynamics. So why even talk about this? So hydrodynamics is, of course, a very well-established field with a venerable history and many applications. But today we'll not talk about applications. Rather, I would like to highlight some foundational questions that only came to light in the last few years. So I'm a theoretical physicist, and actually a better title for my talk would be Hydrodynamics, a theoretical physicist's perspective. But it will not be a technical talk, it will be a colloquium. So what is hydrodynamics? So it is basically a set of equations that tell you how stuff flows. So stuff can be water, air, can be a cold atomic cloud, could be hot primordial matter in the early universe, can be electron fluid in a solid. I remember being a student who studied hydrodynamics, and as a student you open a book that has hydrodynamics or fluid mechanics in the title, and you often see derivations, approximations, applications, and everything will be mixed together. You jump from one to another, and it's kind of hard to follow. And if as a student you're also learning about vector calculus and partial differential equations at the same time, then it can be hard as a student to see the big picture. But the big picture of hydrodynamics is, in fact, quite simple. Hydrodynamics is essentially about stuff that is conserved. So it is a macroscopic theory of things that cannot disappear. And the way we write conservation laws in physics is like this equation in the center. That's how we teach our students about conservation laws. So in the left-hand side, you have the time derivative of some conserved density, that I call little a. And in the right-hand side, I have the divergence of the flux of the same conserved density. So we write down this equation when we tell our students about charge conservation in electrodynamics. We write the same equation when we talk about the conservation of probability in elementary quantum mechanics. Of course, we write down the same equation when we talk about the conservation of mass in fluid mechanics. So pretty much every time you have a conservation law in physics, it looks like that. So then second ingredient that goes into hydrodynamics is what people call the constitutive relations. So what is it? So let's look at our conservation law. So you have 4 unknown functions, say in 3 dimensions. 1 unknown function, which is the density, and 3 components of the vector, which is the flux. Right here. I don't know if you can see my mouse. Can you see my mouse? Yeah. Right. So you have 4 unknown functions, and you have 1 equation. Now, if you assume that the flux here in the right-hand side is a function of the density, some function of the density. Then you have one equation for the density, and that equation you can presumably solve. So this relationship is what people call the constitutive relations or the material relations. So more generally, we can take some useful quantities, such as temperature or the fluid velocity or whatnot, and express the density in the left-hand side of the conservation law as a function of that useful quantity. And we can also express the flux in the right-hand side of the conservation law as a function of that useful quantity. And then we have equations for our useful quantities, which I'll call gamma here, and we can solve them. So here is a very simple example. Let me take my conserved quantity to be the energy, and my useful quantity to be the temperature. Then in the left-hand side of the conservation law, I have the density. Now it will be the density of energy that I have to write as a function of temperature. It is something that is given by the equation of state. In the right-hand side of the conservation law, I have the flux. And the flux is a vector. And my useful quantity is temperature is a scalar. In the simplest way to make a vector out of a scalar is to take the gradient. So that's what I'm saying. I'm taking the gradient of temperature to form a vector, and I stick out some coefficient out in front. This coefficient is the heat conductivity. Right? And then it's pretty clear that when we look at small deviations from equilibrium, T is equal to some background plus delta T, we obtain a diffusion equation for delta T, right? So it's clear you have one derivative, time derivative in the left-hand side from the time derivative of density. And in the right-hand side, you have two derivatives, one coming from temperature here and one coming from the divergence of the flux. So you have two derivatives in the right-hand side. So that is the diffusion equation. So that is how you obtain diffusion equation. So that was just a simple example. And here is a summary. So hydrodynamics is about two things: conservation laws, the constitutive relations. As you have seen, the constitutive relations can depend on derivatives of our useful quantities, as we have seen in the example of diffusion. And in general, density and the flux have these functions of derivatives. And this general procedure of combining the conservation laws with the material relations is exactly the same, whether your fundamental constituents of matter, whether classical, quantum, relativistic or non-relativistic, normal fluid, superfluid, have magnetic fields or no magnetic fields, chiral fluid, no chiral fluid. The general procedure works exactly the same like is written on this slide. So that's the big picture of hydrodynamics. So I talked about derivatives here. We often make various simplifications for fluids. If you just take by hand and throw away everything in your constitutive relations that have derivatives, just throw away all of those terms, then you get what people call perfect fluids. So perfect fluids give rise to the so-called Euler equations of hydrodynamics. If by hand you throw away all the terms that have two and more derivatives, and you only keep the terms that have no derivatives and one derivative, then what you get is the so-called viscous fluids. The equations are the Navier-Stokes equations of hydrodynamics. If you throw away three or more derivatives, if you keep up to two derivatives, you get second-order fluids that give rise to Burnett equations of hydrodynamics and so on. So this is sort of the big picture of hydro. And like with every theory that we have in physics, we have to ask certain questions. So every theory in physics is wrong, or rather it is only approximately correct, and is limited by its domain of applicability. And whenever we write any equations that attempt to describe physical phenomena, we have to answer the following questions. Do the equations make physical sense? Can we improve the equations to capture more physics? And what kind of physics is outside of our equations, is beyond the equations? And what I'm going to tell you now are three stories, three short stories, one story for each question. Okay, so this is going to be the talk, three short stories, one for each question. So my first story is this. Do hydrodynamics equations even make sense?
So sorry, but when people in statistical physics talk about hydrodynamics, and there's hydrodynamic equations on different scales. There's macroscopic equations where every unit of volume is a thermodynamic limit. There's mesoscopic scales like Landau-Ginzburg. Yep. So it's not clear to me from your discussion what you have in mind.
What I have in mind is the macroscopic equation, is the equation that is closest, is the next simplest thing after thermodynamics. That's the thing. So
every unit element, every element of volume is a thermodynamic limit.
If it exists. If it exists in a certain sense, so I'll come to discussion of what problems may arise from that next. But what I have in mind is the thing that is closest to thermodynamics. These gradients that I have here are arbitrarily small.
Okay, thank you.
Right. So my first question about do hydro equations even make sense? And I want to talk here about relativistic things. So let's say you're a student in subatomic physics or in astrophysics, and you want to learn about relativistic Navier-Stokes equations. Perhaps you want to study the quark-gluon plasma that is produced in nuclear collisions, or perhaps you want to study neutron-star mergers. And you want to learn about relativistic Navier-Stokes equations. And you may want to look it up in the classic textbooks. So when I was a student, all the students were tortured using the course of theoretical physics of Landau-Lifshitz. And for me, the first place to go would be to open fluid mechanics of Landau-Lifshitz. And yes, it has sections. It has a section about relativistic Navier-Stokes equations, and you can see some equations there. Then I was a graduate student in the US, and then you come to the US, you realize there are other books that exist in the world besides Landau-Lifshitz. And I had a copy of Weinberg, Gravitation and Cosmology. And in Weinberg, there's a section about relativistic Navier-Stokes equations that I was reading. And these equations are actually different. So the equations that you see in Landau-Lifshitz are actually different equations from what you see in Weinberg's book. And what you see in Weinberg's book is hydrodynamics as formulated by Eckert in 1940. So the equations look different, so what? So as a student, you're taught to shut up and calculate. And let's shut up and calculate. Let's do the simplest possible example, that is to solve for the linear perturbations of the thermal equilibrium state. And when we do this exercise, it's quite easy to do. When you do this exercise, you will realize that both Landau-Lifshitz's equation and Eckert's equations, they're different equations, but they have two things in common. They predict two things. One, they predict that thermal equilibrium does not exist. That is, thermal equilibrium where everything is uniform is unstable on a microscopic time scale, not on a macro, but on a microscopic time scale. And second thing they predict that things propagate faster than light. Okay, so these are universal predictions of those two hydrodynamic theories. People have known about that since 1960s. I put some references from the 80s where this was emphasized in great detail. So it is sad but true. The equations that you find in the classic textbooks, they make no physical sense. And this has led to the belief that the Navier-Stokes equations cannot be unified with Einstein's relativity, and they have to be abandoned in a relativistic setting. Other exotic theories have been proposed in the 1970s to replace the Navier-Stokes, and the field has moved on. So for example, when you talk to people who literally solve in practice for relativistic viscous fluids, say in the context of nuclear physics, they don't solve Navier-Stokes because you cannot. They solve those theories that I call other exotic models here.
Can you just define what you mean by relativistic scenario? I mean, let's say that I have this flowing river in the woods, and I just look at it from a very fast moving frame. Does it already makes this river relativistic?
No, of course not. So what I mean by relativistic fluids, I mean fluids whose microscopic description is given by constituents that move relativistically, right? So the most important thing about the structure of the fluid dynamical equations is the underlying symmetry principles of those equations, right? And if the microscopic degrees of freedom move relativistically, then the equations that govern those fluids, they have to respect that symmetry, right? So the equations have to transform covariantly, if you wish, under Lorentz transformations, as you go from one reference frame to another reference frame, and they have to be formulated in terms of quantities that transform covariantly under Lorentz transformations. So the mathematical structure of the relativistic equations will be different from the normal, say, Galilean fluids that you use to describe the normal non-relativistic fluids. If you simply just make a boost, of course, it does not make a fluid relativistic. But even if you look at infinitesimal perturbations of a relativistic fluid, that is fluid whose constituents are relativistic, they what you will see may actually look very different from what you see in normal Galilean fluids. To give you a simple example, let's look at an example. For relativistic fluids, you do not even need to have the notion of a conserved number of particles. Of course, mass is not conserved. Number of particles is not conserved. So the vanilla relativistic fluid dynamics equations are only equations that tell about energy and momentum conservation. Now, if you have normal Galilean fluids, you cannot do away with just conservation of energy and momentum. You must include the conservation of mass, right? And all of these equations are now going to be mixed together, right? So this is one way how you can see that relativistic equations may be very different from non-relativistic ones. Does this make sense? So, so why do theories of Landau, Lifshitz, and Eckert, why do they differ in the first place? So to understand why, let's talk about temperature. So I'll let you read this this cartoon here. Okay. So temperature has units. Measurement of temperature is important. So when we teach our students statistical physics, so we tell them that temperature is only something that is unambiguously defined in equilibrium. And by definition, temperature is the quantity that is measured by a thermometer. So what I have here is a cartoon of two identical equilibrium states. So I have a box, and this yellow stuff is my equilibrium state. And what I have in the box are two different thermometers. These are little heat reservoirs of those thermometers that are coupled to their gauges. And in identical equilibrium states, these two different but properly calibrated thermometers, they will show the same temperature. Now, if you take the same two thermometers and place them in identical non-equilibrium states, the same two thermometers will now show different temperatures, even though they used to show the same temperature in equilibrium. And we know this very well when we have maybe two different thermometers outside our window. If the wind blows or temperature changes, one of them maybe will have different time to adjust to the temperature changes than the other thermometer. So out of equilibrium, these two thermometers will give you different readings, even though they give you exactly the same readings in equilibrium. So what this tells you is that there is an arbitrariness in what we mean by fluid temperature. And that is because our choice of a thermometer is a convention. You can choose one thermometer, I can choose another one, it's a convention. There is same arbitrariness in what you mean by fluid velocity, because your choice of a velocimeter is a convention. And Landau-Lifshitz version of Navier-Stokes uses one convention, and Eckert's version of Navier-Stokes uses a different convention. So that is why these equations are different. And so what this also tells you, that there is no such thing as quote unquote the Navier-Stokes equations unless we specify, or rather until we specify our arbitrarily chosen convention. There is an intrinsic degree of complete arbitrariness in what we mean by Navier-Stokes equations. And what is very important is that different conventions, they give rise to different, that is mathematically inequivalent Navier-Stokes equations. It's not a typo, I do mean inequivalent. So the conventions have real consequences. Of course, hopefully, all these different equations give the same answers within the domain of applicability of hydrodynamics. But as mathematical equations, you can have different equations. And so They're mathematically inequivalent because the Navier-Stokes equations only give you a crude approximation of a real fluid. The difference between the conventions is hidden in the crudeness of this approximation. Landau, Lifshitz, and Eckert, they adopt different conventions, but both are bad, and both lead to nonsensical predictions.
So could you elaborate? I'm going back to what I asked before, but if every element of volume is a thermodynamic limit, and it's an equilibrium at this unit element of volume, then why can't I define temperature systematically?
Or precisely because of that, different thermometers will give you different readings in equilibrium. Give you different readings out of equilibrium, right? So if two different observers choose to use different thermometers, there is no way that to make it work unless you are exactly in equilibrium.
Okay, thank you.
So maybe in terms of velocity, it is it's maybe to give another example, maybe in terms of velocity. When people talk about the velocity of a fluid, it's not exactly clear what we mean when we talk about the velocity of a fluid. Do we mean the velocity according to which the particles in the fluid move? Or do we mean the velocity according to which the energy of the fluid moves? Or do we mean the velocity according to which the entropy of the fluid moves? I mean, they're all different definitions of what we mean by quote unquote velocity of a fluid out of equilibrium. And if we use those different definitions of velocities to write down the Navier-Stokes equations, they will give rise to different Navier-Stokes equations. So in this example of Landau, Lifshitz, and Eckert, so what exactly is wrong with the classics? So talking about temperature, if you look at what the classic treatments do, they do this. Both Landau, Lifshitz, and Eckert, they define temperature by the following relation. They say that the exact non-equilibrium density of energy is equal to E of t, where this is the function given by your equilibrium equation of state. Okay, so that's the convention that they adopt. Now remember, the non-equilibrium density of energy is something that is a physically fundamental quantity, right? In quantum mechanics, there exists an energy density operator. We can take its expectation value in any non-equilibrium state. It's a local quantity at every given point in space-time. We can, in principle, define what we mean by the density of energy, can calculate this if we are smart enough. Now, T is not microscopic. T is just temperature is just a proxy for energy. But this is a convention that they adopt. And what this convention means, it means this: as the local energy density changes, the temperature, the thermometer adjusts its temperature instantaneously, just like that. The reaction is immediate. And it turns out that such thermometers violate relativity, and they lead to superluminal propagation in relativistic fluid dynamics. So, well, you can say, wait, why don't you choose a thermometer or velocimeter that does not react instantaneously and respects relativity? So can you just adopt a sensible convention? And a few years ago, people figured out that yes, you can. With good conventions, the equilibrium is stable, signals propagate slower than light, the equations are mathematically well posed, and they can be coupled to Einstein's equations. So this is really a development of the last few years. So the bottom line for my first story is this. So unifying Navier-Stokes with relativity was thought to be impossible for many decades. But you just need to choose a physically sensible thermometer or velocimeter. And then the Navier-Stokes equations, indeed, they can be unified with relativity. They're still waiting to be solved. Numerical codes have not yet been written for those equations. So that's something that's coming in the next few years. However, from what I have said so far, there is also a question. And the question is this: the parameters of my thermometer or velocimeter, they need to be present in the equations. in the hydrodynamic equations. And this seems to be a universal feature of every single relativistic hydrodynamic theory that people know about. So sensible relativistic hydrodynamics seem to require that the equations contain non-hydrodynamic parameters. So this is different from the conventional Navier-Stokes, from Galilean Navier-Stokes. For Galilean Navier-Stokes, you only have thermodynamics and the viscosity and the heat conductivity. But here it's different. The equations must contain non-hydrodynamic parameters in order to make sense. Now, if your equations contain non-hydrodynamic parameters, this means that your solutions to those equations will depend on those non-hydrodynamic parameters. And you can choose one convention for those non-hydrodynamic parameters. I can choose a different convention. We will potentially get different answers that hopefully will be the same within the domain of applicability of hydrodynamics. But is it really so? Does hydrodynamic equations actually have predictive power? I don't know the answer to that question. Some aspects of this question also exist for normal non-relativistic Galilean Navier-Stokes. If people in the audience have thought about this, I would love to hear. Your thoughts on that. So this is the end of my first story. So my second story is this: are there limits to improving the?
I'm sorry, can I ask a question?
Yep.
So what do you mean by these non-hydrodynamic parameters? Can you give an example to be specific?
Right. So as an example, for example, if you look at this relation here, so this relation clearly has to be modified in order to give rise to equations that are sensible. And what every single theory of relativistic hydrodynamics does that gives rise to sensible predictions, it introduces some kind of relaxation time for temperature here. This relaxation time can be related to the parameter of your thermometer. It can be just thrown in by hand, but there's some kind of relaxation time that sits here. So this relaxation time is something else. It's not the viscosity. It's not the heat conductivity. It's not something that is calculable microscopically from the Boltzmann equation or from Kubo formulas. It's not something that's calculable. It's really an extrinsic thing to the theory. This relaxation time, which can be related to the property of the thermometer. So it is this thing that I have in mind when I talk about non-hydrodynamic parameters.
So I have an even simpler question. So why do you insist on using temperature as a parameter of your theory? Why not use just the energy density?
Excellent question. And that is, so in a non-relativistic setting, you can do so. In a relativistic setting, if you want to write down equations that are covariant, energy density is not a scalar. So energy density does not transform covariantly under Lorentz transformations. So if you want to have a quantity that does transform covariantly under Lorentz transformations, you need a scalar. And temperature is my proxy for that scalar. So it's related to the symmetry.
I must admit, I'm a little confused, if you don't mind. We, in astrophysics, for example, where people solve these relativistic stuff, everything seems to be well defined up to the transition between the microscopic and the macroscopic. Meaning, if you look at a fluid element of some certain size, you define there the quantities which you need. For example, we may have temperature equal 0, and yet we have pressure, and we have a well-defined, as much as physics as we know how to calculate, equation of state. So I'm not sure why everything you say here is just probably you are saying it is just a matter of convention. It has nothing to do with physics.
So I'm talking specifically about viscous fluids. Do you, when you mention the examples that you solve in astrophysics, do you have in mind perfect fluids?
No, not necessary. It could be any type of matter that is flowing. I mean, it's not necessarily that. It doesn't need to be. Radiation also, it may include radiation. As long as you have a set of equations governing the quantities which are to be conserved, then you go on. It seems to me you're insisting on constituency. How did you call the constituency relations?
Yes, yes.
And we don't insist on that.
No, you must insist on that.
I know you insist on that, but when we work with these equations, we say, okay, what is going to be the expression for heat conduction? And that it could be through radiation, could be through anything you want.
Yes. But what you see, you must have these constitutive relations. Otherwise, these conservation laws don't tell you anything, because you have one equation and you have more unknowns. You have the density and the flux. You have more unknowns than you have equations. Otherwise, you cannot do anything.
Follow the math here, but when we solve these equations, when we go to the code, the physical code, and write the equations,
yeah,
we think about how to relate, for example, the energy density. You write a conservation law to the microscopics of the system.
Mm-hmm.
We're not thinking about what you're saying now, and it is strange to me that you are getting different answers. The different answers you're saying you're getting don't seem to be just a matter of expressing things in different variables, like the example which you mentioned in the velocity, that you would velocity with respect to propagation, with respect to the gas itself. So all this just a change of variables, isn't it?
It is true. It is so there are two things, right? So one is the change of variables, but this change of variables has to be done within the framework where you truncate the expansion, right? Because you never go all the way to the infinite order. So, and once you do a change,
I see now. You're saying that in one limit, if I go to one variables, then it's enough to go to gradients. If I go to the other one, I need to go to the second derivative.
Perhaps.
That's the mathematics. Oh, that's okay. That's just a matter of doing the right formalism,
right. Now, another thing that I want to emphasize here is that when I look at these equations, I do not want to specify to what is the microscopic theory that I'm considering. So these equations are completely agnostic to any microscopic theory. If you can calculate things with your microscopic theory, who needs hydrodynamics? Really, just let's calculate things with microscopic theory. Now, if I have some strongly interacting quantum fluid that has, no concept of quasi-particle whatsoever, the notion of Boltzmann equation makes no sense, then hydrodynamics is the only thing that you have. If you have really access to microscopic calculations that you can trust, then hydrodynamics is just a macroscopic theory that you may not need simply. Yeah. Right. So my second story is this: are there limits to improving the hydrodynamic equations? So here is my first look at the limitations of hydrodynamics. And what I have here is a cartoon of microscopic degrees of freedom. They have some typical distance between them that I call little l, microscopic scale. And what I have below here is a cartoon of the solution to my hydrodynamic equation. So this thick blue line is a solution to my Navier-Stokes equations, and it comes with its own distance scale, which I'll call capital L here. That's a temperature as a function of distance. And hydrodynamics, you would think it's probably okay if this capital L is much smaller than this little l. So in other words, at least it's necessary, may not be sufficient, but at least it's necessary that the derivatives here are small. So this is what, right? So this is what I will assume about hydrodynamics. On the other hand, if you solve your hydrodynamic equations, and if you find a solution that looks like this, that is, you find solution whose macroscopic variables change on a distance scale, capital L, that is comparable to this microscopic scale, of course, you should not be trusting this, right? You should not be trusting your macroscopic equations for the predictions on the microscopic distance scale. So hydrodynamics is probably not okay when capital L is same order as little l when the derivatives are large. And this suggests that you organize hydrodynamics as an expansion in derivatives. Whether this is true or not, Okay, we can talk about this, but let's make a first assumption that you can do this. And so then my constitutive relations will look like this. So I have something that I call superscript 0, something that has no derivatives of my variables, of my useful variables like temperature, velocity, plus something that I call superscript 1 that has one derivative of my temperature, velocity, whatnot, plus something that I have two derivatives of my temperature, velocity, and whatnot, plus ... So the first thing here is what you call perfect fluids. Of course, these are the most imperfect model of fluids. They cannot flow through a pipe. Sound propagates forever. Diffusion does not exist. Second thing here is the Navier-Stokes fluids is an improvement of the perfect fluids. You introduce dissipation and restore common sense. Then you have second order fluids. It's an improvement of the Navier-Stokes equations that you can imagine. You can do this. You can keep going on and on and on. So let me ask this question. Can you keep improving forever? So let's say you generate an infinite series in the gradients. Does this series converge? As in this example that we teach our students 1 over n squared. So this converges. Or does the series diverge? As we teach our students in this example, when you sum 1 over n, you get an infinity. And if the series converges, then hydrodynamics can be systematically improved to include more and more transport phenomena. So we have hope. And if the series diverges, then hydrodynamics is not even supposed to work. But then it does appear that it works. So why does it? Is hydrodynamics a fluke? So I want to make this precise. I want to talk about what exactly is the expansion. So let's look at simple examples of plane waves. And if you have a plane wave, then the derivatives is just I times k, the wave vector, when you differentiate the plane wave. So the hydrodynamic expansion is an expansion in powers of k, of your wave vector, of your momentum. For example, you look at the dispersion relation of the sound wave that we teach our students in elementary classes about waves. It has the first term, Vs is the speed of sound, k is the wave vector. Now it has a second term that is proportional to k squared. There is this coefficient gamma that is proportional to the shear viscosity, or shear and the bulk viscosity, two of them, of the fluid. It is imaginary, it describes dissipation. Then you have plus ... So the simplest question you can ask when you ask about the convergence of these expansions is the question, do the series, say dispersion relation, frequency is a function of k plus k squared plus k cubed plus so on, do the series converge or do the series diverge? And to answer this question, in practice, what you need to actually compute these coefficients, a, b, c, d, and so on, all the way to infinity. Now, computing these coefficients is not easy. So a is related to the equation of state, but b is the computation of viscosities. And even in a gas of weakly coupled quasi-particles, computation of the shear and bulk viscosities is not a trivial exercise, especially if you want to do it from fundamental quantum field theory with quantum particles. I mean, it's a pain to do this. And this k cube and so forth, they will be complicated things. So I don't know how to answer this question in general. I'll look at examples, simple toy models where this can be answered. So there are some analytic examples where you can answer these questions. There are fluids that can be studied analytically using so-called holography. So holography is just a mathematical trick to exactly solve certain kinds of fluids. These fluids that are more or less similar to the quark-gluon plasma that are produced in nuclear collisions. They look like black body radiation, except the photons in the black body radiation, they have strong quantum interactions. Okay. And in the simplest solvable examples of such fluids, we found that the dispersion relation of sound waves, they're actually analytic functions of k convergent up to certain wave vector, critical wave vector, whose value is determined by temperature, h bar, Boltzmann constant, speed of light, and so on, some nice constant square root 2 pi, and so on. So we found convergence in those toy models. So this convergence is important. It gives me hope that hydrodynamics is improvable. So, but what I want to talk about here is I want to talk about why there is convergence, why there is a critical value in the dispersion relation. And to understand why, it's easiest to look at this example from basic math. So let's look at a function that looks like function is equal to 1 divided by 1 plus x squared. So this function is a perfectly smooth function of x. So I have a plot here, okay? And if you look at the Taylor expansion of this function, when you expand this function as a power series in x about the origin, you realize that this expansion only converges when absolute value of x is less than 1. Now you look at this plot here, 1 is here. The function is perfectly smooth. Nothing is singular. All the derivatives exist. So why does this Taylor expansion only converge when absolute value of x is less than 1? And of course, as we teach our students, to understand why, we need to take x complex. Because the moment we take x complex, we realize that this function has no singularities on the real axis, but it has singularities in the complex plane. When x is equal to plus minus I, the function is singular, and the distance from the origin to I is equal to 1. So the radius of convergence here is 1, because 1 is the absolute value of I. And similarly, what happens with these dispersion relations is that omega of k is a smooth function of real k. And to understand why it only converges for some up to some critical value of k, you need to take your wave vector complex. So let's talk briefly about complex omega and k. Okay. So in classical physics, dispersion relations, omega is a function of k, they came about by solving equations like this. Some function of omega and k squared is equal to 0. This capital function f, capital F, is determined by the equations that you solve. Hydrodynamics or Maxwell's equations in matter or some other macroscopic equations. For example, in the example of diffusion that I gave, this capital F looks like this. So it's pretty clear, right? So you differentiate once with respect to time, you get minus I times omega for a plane wave. You take two derivatives with respect to x, you get minus d times k squared. So this is your capital F for diffusion. For sound waves in a viscous fluid, it looks slightly more complicated. You know, there's frequency here, speed of sound here, k squared. And then there is some damping here that is proportional to the viscosity. Okay. Now, when we talk about waves in physics, we usually do one of two things. One thing that we do, we say, oh, let's take omega frequency to be real. And then if we want to solve those equations, like when we talk about, you know, propagation of waves in conductors, when we solve this equation, you find k as a function of omega. And then you will realize that you can only solve this equation if k is complex. If omega is real, you can only satisfy this equation if k is complex. And the imaginary part of k, it has a physical interpretation of the damping length or the penetration depth of the wave that propagates inside the material. Another thing that we do in physics when we teach our students is we tell them, oh, let's take k real. Then when we solve this equation, you find omega is a function of k, and omega will be in general complex. Then we interpret the imaginary part of omega as the relaxation time of the wave. Now, so those are the two things that we do normally when we teach our students. Now, but what if both omega and k are complex? Right, this is not something we usually talk about when we talk about waves. We don't talk about both of them complex. So what I want to talk about both of them being complex. So what I have here, I have a picture that shows oscillation modes of a fluid at real k. So this picture comes from those toy models that I was talking about. These are quantum liquids that you can solve exactly using these mathematical methods called holography. And what I have here is a plane of complex frequency, real part of frequency, imaginary part of frequency. My frequency is measured in the units of temperature. There is some h bar here. And each dot here is a solution to this equation, f is equal to 0 for my toy models in the plane of complex frequency. And this q here, q, is my wave vector or my momentum measured in the units of temperature. So each dot here corresponds to an oscillation mode of a fluid. Now, these two dots here that are closest to the origin, they're sound waves. these are macroscopic excitation that are describable by hydrodynamics. The classical excitation, as you take k to 0, they approach the origin. There are two of them on the left and on the right. That's because sound waves has dispersion relation with plus minus speed of sound times k. Your waves can propagate to the left or to the right. And this distance, this imaginary part of this of these dots, they correspond to dissipation. Right? So this distance here is determined by the viscosity. Okay. Now, what about the other dots? The other dots are microscopic oscillations of the fluid. They have no classical interpretation. They stay away from the origin as the wavelengths become larger and larger.
So we haven't seen the equations, but if you have something describing microscopic oscillations, so don't you expect some noise to enter the equations from the chaotic dynamics or something along these lines? It doesn't look like just a deterministic equation anymore.
No, these are equation of a quantum liquid. So the underlying degrees of, it's not a classical theory, it's a quantum theory. It's similar to the black body radiation of photons, except photons interact very strongly to the extent that it washes out all notions of quasi-particles. However, it is a model of a certain, these models of a certain type that people call large N models. And these large N models, they suppress certain kinds of fluctuations. So in the last part of the talk, if I get to it, I will talk about those fluctuations. But for now, so those fluctuations, they would give rise maybe to branch cuts in this plane of complex frequency. But in the models that I'm looking at, there are no branch cuts. In this so-called large N models, these branch cuts are suppressed.
Okay, thank you.
Right. But again, the fluid is not a classical fluid. It's really a strongly interacting quantum fluid, and these are actually quantum microscopic excitations. So now I want to look at oscillation modes of a fluid at complex K. So Q here is my wave vector measured in units of temperature. And what I'm going to do now, I'm going to make my wave vector, and I'm going to make it complex. Okay. So this picture that you're looking at right now is the complex frequency plane when the wave vector is real. Now I'm going to take my k squared, and I'm going to give it a phase. And I'm going to change that phase from 0 to 2 pi. And as the phase of my wave vector, or rather wave vector squared in this picture, changes from 0 to 2 pi, each dot here will move in the plane of complex frequency. Okay. And when the phase becomes equal to 2 pi, the spectrum has to come back to itself. Of course, the whole picture, has to look the same. So this is the phase is equal to 0. Now I'm changing my phase from 0 to 2 pi. They move, and here is the phase is equal to 2 pi. Okay. So just to do it again. So here 0, and now it's 2 pi. And what you see has happened is that the two sound waves, they have swapped places. So it's easier to understand why that happens, but they swapped places and they remain sound waves. So that's not that I want to emphasize. I want to emphasize something else. So now I want to see how my modes of a fluid, how they move in the plane of complex frequency when my wave vector is 1.99 in the units of temperature. Okay, so this is when the phase is equal to 0. Now I change the phase from 0 to 2 pi, and now they move, and now this is phase is equal to 2 pi. Okay, so sound mode, this blue and the gold, they swap places, but still remain sound modes when theta becomes equal to 2 pi. Now, if you take the limit of long wavelengths, they will approach the origin. They will stay the normal sound waves. Now, my last movie here is when my wave vector is equal to not 1.99, but when is it equal to 2.01 in this units of temperature. So when the wave vector is equal to 2.01, The phase changes from 0 to 2 pi, and that's what happens. This is my phase equal to 2 pi. So what you see has happened here is that this gold one, it used to be a sound wave. Now it has swapped places with one of the non-classical modes. Now, if you take the limit of long wavelengths, it is these two oscillation modes, the blue and the green, that will become sound waves. So what used to be a non-classical excitation now became a classical excitation that is describable by hydrodynamics as the phase has gone from 0 to 2 pi. So these pictures here, they show you the same information as you have just seen in the movies. So these pictures here show the trajectories that are traced out by the oscillation modes of the fluid in the plane of complex frequency. Right? If you look at this orange mode here, it kind of makes a loop here and comes back to where the sound wave used to be when the momentum is small. And in this picture on the right, it kind of swaps places with one of the non-hydrodynamic modes when the momentum is large. So what you're looking at here, you're looking at something that has to happen in between 1.99 and 2.01. And what happens is the collision of singularities. The modes collide, and the topology of those trajectories changes. So what you were looking at, you're looking at level crossing, but this is level crossing in macroscopic dissipative systems, not the level crossing in quantum mechanics as we teach our students. This is level crossing in macroscopic dissipative systems, when a classical hydrodynamic excitation that is describable by classical hydrodynamics equation, it becomes exchanged with a non-classical excitations that is invisible, so we thought, to hydrodynamics. And so this collision of singularities is what determines the convergence of the hydrodynamic expansion. So this is what gives the critical wavelengths for sound, determined by the temperature in these examples. Okay, so this is cool, but there is more to complex momentum. So I just wanted to mention this briefly. So this is not my work, but I think this is very nice. So this is the relationship between complex momentum and chaos. So what is chaos? Chaos, well, different people mean different things by chaos. Chaos is roughly how microscopics gives rise to macroscopics. And in classical mechanics, one way to describe chaos is through Lyapunov exponents that describe the divergence of phase space trajectories. So delta x is the difference between your trajectories in phase space. And as time goes on, the deviation grows exponentially. This coefficient lambda, people call the Lyapunov exponent. There exists a quantum analog of this Lyapunov exponent that can be viewed as the commutator, the expectation value of the commutator squared. And there are arguments that in these chaotic systems, the expectation value of the commutator squared, again, grows exponentially with time as e to the 2 lambda times t. Now, here is a very, very kind of dumb thing that you can do. The dumb thing is this, quote unquote. You can take a plane wave, and let's take my frequency to be purely imaginary, I times lambda, some lambda, and k is I lambda over v with some v. And if you just make the substitution into a plane wave, you get something that grows exponentially in time, like this. And actually, it turns out that in those exactly solvable models, the sound wave dispersion relation, when the frequency is purely imaginary, it passes through this point that gives you the Lyapunov exponent. So it is explained in more detail in these papers. But what it looks like that when you look at the dispersion relation of sound at complex momentum and complex frequency, you are able to extract the Lyapunov exponent from the hydrodynamic dispersion relation. Now, why is this? I don't know. There are some arguments based on effective field theory, how people attempt to describe this. but I think it's quite cool, quite nice. Again, it's probably limited to a certain class of examples, not so universal, but still nice. So the bottom line is that in many solvable examples, classical microscopic excitations, macroscopic excitations, and non-classical microscopic excitations, they're merely different branches of the same multi-valued complex function. And in many solvable examples, classical hydrodynamics at complex momentum knows about the quantum Lyapunov exponent. Okay, so this is the end of my second story. Now, I also have a third story, which is why everything I said so far is wrong. Now, unfortunately, I don't have much time to talk about the third story, so I'll skip briefly, maybe to this slide. So, in the third story, I want to talk about the phenomena that maybe were alluded to in one of the earlier questions. So here is an example of viscosity. So viscosity tells you about how the fluid flows from right to left. So the x component of the velocity has dependence on y, and so dy vx is non-zero. The relationship between the stress txy, remember, stress is the flux of momentum. The relationship between the flux of momentum and the y derivative of the x component of the velocity has this linear form. In hydrodynamics, there is some coefficient out front, which is the shear viscosity. And what I have here also in the cartoon are these blue arrows. These blue arrows, they represent particles that jump between the layers of your fluid. And as they jump, they transfer momentum. And what you see, if this distance by which they jump is large, they can transfer momentum very, very efficiently, say from a very fast moving layer here to a very slow moving layer here. And in an example of a gas like this tells you that the viscosity is actually will be proportional to the mean free path. Now, the second cartoonish picture that I have here is this. Momentum can also be transferred by collective excitations. Statistical fluctuations, they will excite sound waves in your fluid. And in a gas of sound waves, this mean free path of sound will be inversely proportional to momentum, of course, because long wavelengths dissipate weaker, and it will be inversely proportional to the viscosity. Now, if you want to now think about the contribution of the sound waves here, the contribution to viscosity, you have to sum over all of those sound waves. When you sum, you integrate over all possible momenta. You integrate dk in d dimensions. And what you realize when you do this integral, well, if you're in 3 spatial dimensions, okay, so this integral is divergent. So you cut it off at some microscopic scale, like microscopic distance scale, interparticle scale, but it's inversely proportional to the viscosity. But if you're in 2 spatial dimensions, this integral is infrared divergent. It's divergent at small k. Now, this is bad. This tells you that what you thought was viscosity is not what you think viscosity should be. So viscosity, the concept of viscosity probably does not exist. So how do you describe these kinds of phenomena? So there's an old way and there's a new way to describe these things. In the old way of describing these things, people describe this using stochastic differential equations, the Langevin type of equation similar to the Brownian motion. Now, however, there is also a new way to think about this. And the new way to systematically describe all these kinds of phenomena and much more is to think about these processes like you think about in quantum field theory in the standard model of particle physics. So you have an action in terms of cleverly chosen variables. They're cleverly chosen such that the Euler-Lagrange equations are the conservation laws. The fluctuation dissipation theorems are imposed by the symmetry. Time has to run backwards and forwards for some technical reasons. But anyway, there is a sophisticated field theoretic procedure to deal with those things. Several groups have worked out the details of this mathematical theory in the recent years. You may recognize Amos Yarom from the Technion, his former postdoc, and Natasha Pinzani here. Anyway, I'm running out of time, so I'll stop here. So where does this leave us? So for many years, I had this dream of a grand unified theory of hydrodynamics. That would be a theory that applies to many different kinds of fluids. It ensures that the equations are sensible, mathematically well posed, like I was talking about in the first part of the talk. It allows for systematic improvements like the derivative expansions, non-Gaussian noises, and so on. It correctly predicts macroscopic correlations and connects with quantum chaos and is experimentally verified. And based on those field theoretic approaches to hydrodynamics, it looks like it's this grand unified theory is close to becoming true. And I find it ironic that just like in grand unified theories of particle physics, they seem to require supersymmetry. So these grand unified theories of hydrodynamics, they also require supersymmetry. So I would like to end with an encouragement. So as a student, one often tends to think that all interesting questions in physics have already been answered many years ago by the great. Hydrodynamics is an ancient field by modern standards, and people are still trying to figure out some very basic questions. So if, as a student, you work in a field that is less than 200 years old, do not lose hope. There are surely many fundamental things left for you to discover. Thanks a lot for listening. Sorry to go over time.
Thanks a lot for this very interesting talk. So I have a few questions, but maybe first I'll ask for others. Okay, well, so first, okay, I have a couple of questions. I mean, one when you say that you need supersymmetry, I mean, so in this program, in what sense do you need supersymmetry? Just I mean, just to make them. I mean, without supersymmetry, you couldn't maybe solve equations. But is it really a requirement?
Well, you probably should ask Amos this question, because these papers are about implementation of supersymmetry. But this hints of supersymmetry you can already see. You can already see when you look at even at the Langevin equation for the Brownian motion. When you look at the Langevin equation for Brownian motion, if you convert stochastic differential equations to the path integral, then as a result of doing so, you have to exponentiate a certain determinant. And you do it using fermionic fields that people call ghosts. And now the action has a certain symmetry that involves those ghosts that you find by exponentiating the Jacobian. And you find this even, again, for the simplest example of the Brownian motion. And so it's kind of a more sophisticated version of the same supersymmetry that seems to be needed in order to describe stochastic dynamics.
Okay, and then the other question I had is, so you gave this criterion for hydrodynamics to be improvable, that was that, this series converges. But in principle, if the series was just asymptotic, it still would make, just like perturbation theory and field theory, field theory can be asymptotic and still be useful. Mm-hmm. Wouldn't that be enough if the series, to use the series as an asymptotic series?
In principle, yes, it would be enough. And in other examples, other examples of expansions, people have found asymptotic expansions of of the derivative expansion. So this will be not in this example that I talked about. This would be in the example of a relativistic fluid undergoing a boost invariant expansion. People call it Bjorkan expansion. It's basically a simplified ansatz to solve the hydrodynamic expansion. And in that Bjorken expansion, which seems to be relevant for how the fluids behave in the nuclear collisions, you do indeed seem to find asymptotic expansions. Now, so the reason I don't quite like asymptotic expansions in this example is this. If the expansion is asymptotic, there should be a reason why it is asymptotic. Okay, so if it is convergent, then we sort of I want to understand the analytic structure of this function. So if the series is asymptotic, how should I think about the analytic structure of, say, my dispersion relations of the complex in the complex frequency plane? Does this mean there are some essential singularities that I don't know about? Does this mean there are some branch cuts that I don't know about? And if those singularities that I don't know about, if they are there, well, how do I get to them? What kind of physics do they describe? So for me, then this would be more questions than answers. Yeah.
Okay, thank you.
Yeah, can I ask also a question? Yeah, so I think there is an additional problem which you can see from astrophysics, that when you have actually relativistic fluid or particles, the relaxation time tends to be very long, because the coupling of relativistic particles is much slower if you talk about at least diffuse gas. And then the whole idea of a thermodynamic description may not be valid in the sense, for example, that if you take in irregular thermodynamics, the temperature tells you the mean energy. So, and the microscopic description is Maxwell-Boltzmann. When the fluid is relativistic and is not really has the time to reach relaxation microscopically, then a given mean energy can actually may be or imply different microscopic distribution of energy of particle distribution. It's often a power law distribution, and the nature, the microscopic property can vary for a given macroscopic number. So it's not that you have a one-to-one transformation from the microscopic description to the macroscopic one. So the whole idea of having a hydrodynamical description may not be valid. I'm not sure what happens inside the neutron stars, and let's say when they collide with each other, it could still be that indeed there is not enough time to reach relaxation, and then we'll have to go to the microscopic level and figure out and solve it. So that could
right. So it depends, of course, on the microscopic dynamics and on the time scale that you use, on the time scale on which you apply hydrodynamics, right? So if the interactions are sufficiently weak so that the mean free path is large, but if you are studying the processes whose of course, distance is scale is much larger, and if you have enough time for these processes to equilibrate, which may or may not be relevant for the physical process that you're interested in, then of course this flies out the window. Hydrodynamics is simply not a good description. Now, on the other hand, if the interactions are strong, as would happen for nuclear matter, I would imagine that. But again, even for neutron stars, I don't know much about what happens there. But the little thing I do know is that different particles have different mean free paths, right? Neutrino is one thing, electron is another thing, and your neutrons is yet another thing, right? So for some of those things, you may have a hydrodynamic description, but not for others.
Yeah. So my tip is that it will be useful. Since the question is whether this is a physical discussion or a mathematical one. if it's a physical one, you need to find for which system it is indeed relevant. So the time scale are indeed allow to get MHD description of a relativistic system.
Right. So for, at least for nuclear collisions, there is a lot of evidence that indeed a relativistic hydrodynamics with viscosity is the right description of the subnuclear matter. For dynamics of neutron stars, the very indication that viscosity may be relevant there is a very recent developments. And people have not yet studied numerically the viscous effects for cold and dense nuclear matter of neutron stars. This has not been explored yet.
Okay, thank you.
Can I ask, since this is supposed to be, if I understood correctly, both relativistic and quantum, what about entanglement?
Yeah, but this is also finite temperature, right? This is also, I mean, this is, if you wish, in the limit of high temperature, where everything has decohered. So in these examples that I looked at, the coherent quantum phenomena would not be visible. Can I study, using these toy models, can I study examples of fluids, macroscopic fluids, where macroscopic quantum phenomena would be visible? I don't know. One can study superfluids. So look at the, one can recover Landau two-fluid theory from here. But I don't know if kind of notion of entanglement of the macroscopic wave function can be recovered from this particular toy models that I'm studied. I'm not sure it can be.
Thank you.
Okay, well, so let's thank Pavel again for this very nice talk. So thanks a lot, Pavel.
Yeah, thanks. Yeah, I can stay.
Indeed, a very